watching?
Yeah.
Okay, all right. So you all might have just missed something that I thought was recording because we started recording at the beginning. Anyway, so back to our story. So they shined this beam of light, and it was a rotating mirror. And that light would flash off the mirror, and they'd had another mirror here. And then it would bounce off that, come back, and then back to this point. And this was separated by a long distance. So once they were able to like figure out how to make this mirror rotate, where that light would come back basically in phase with each other. So then they knew the total distance that it had to travel, and then they knew how long it took for it to go based upon the rotation of this mirror. And that basically, since it wasn't a continuous beam, since this is like an octagon-sided mirror, so you would get gaps when there wasn't light, and so they were able to figure out the timing of the gaps, and then they knew the distances, and they were able to figure out the speed of light. And so one of the things that they struggled with was that what was the medium in between the sun and the earth? Because at the time, they thought that this light had to have a medium to transfer it through. Just like if you're in a vacuum, you can't hear sound because there's nothing to transmit the sound. So they thought the same thing had to be happening with light, that there had to be this medium in between the sun and the earth. And they called it this kind of weird, the ether, okay? And so this ether had these really, really weird magical properties. Like, so the earth would be traveling through this ether, but we couldn't feel it. So it isn't like, oh, you're driving down the road and you're moving through our atmosphere and you put your hand out, oh, you feel that. So this ether was there, and it allowed this electromagnetic radiation to be transmitted through it, but yet it didn't impact us on Earth. So it was there, and it allowed it to be transmitted, but we didn't have anything, but it didn't impact the motion of the Earth at all. So it had these kind of weird properties to it. And the other thing they found about the speed of light, and this is where you get into like Einstein's theory of relativity, is that if you look down on the top of the Earth, okay, and the Earth is spinning counterclockwise, and here's the sun, and here's this light coming towards it. So if you're on this side of the Earth, and you're going towards the source of the light, it should have almost been like the Doppler effect, where if I'm walking towards Lauren, and Lauren's walking towards me, then we're effectively closing the gap at a much higher rate than if I'm spinning this way.
Oh. Okay. So. Can you do that?
Greetings.
Teacher Appreciation Week.
Fantastic.
We have snacks and drinks for you.
Did you like the intro?
I did. It was very dramatic.
Pretty patient about it.
It was very dramatic. Okay. So give me a Coke, please.
Coke it is.
And
We have popcorn, chips, cookies, and candy on the bottom.
You already had two cookies. No, it's a
There you go.
all right.
Have a wonderful week, sir. Teacher Appreciation Week.
You should have brought him some Brussels sprouts. He really likes Brussels sprouts.
Shut
Make
it.
sure to bring those.
I think he's waiting on you guys to bring the Brussels sprouts.
No,
Oh,
I'm
we'll
them
do
to
it.
bring peanut M&M's.
Joe,
Oh yeah, I liked it.
YouTube was a little slow on my.
Well, on the boom booms. Yeah. Yeah. So yeah, the joke this morning was my deal. So the joke was, so there was a king who was only 12 inches tall. He made a horrible king, but he made a great ruler.
Oh,
So boom boom.
so funny.
All right. So anyway, so back to our story. So what they thought should have happened was that when the Earth was spinning towards the sun, you should have measured a higher velocity than when it was moving away from the sun, because then you're moving in the direction of that light. What they found is that no matter how you measured the speed of light, you always got the same value. So everybody thought there was a problem with the apparatus. Okay, and the beauty of what Einstein did is he accepted that the speed of light was a constant. Because at the end of the day, what they were doing to calculating the speed of light is that they were taking distance and dividing it by time. So everybody thought this value should change because they thought distance and time were absolute values. Okay? So the beauty of what Einstein did is that he accepted that the speed of light was a constant. And then he said distance and time change. And that's how you always get the same value for that. And that was a huge leap of faith because everybody thought a second was a second was a second. A meter was a meter was a meter no matter how you're measuring. And Einstein basically said, no, depending upon your moving frame of reference, this distance and time can change. The speed of light is what is the absolute value. So we'll get more into that later. But that was part of this idea. So then they said, okay, all right, so we'll accept the speed of light. Okay? 3.00 times 10 to the 8th meters per second. And we've worked with these equations before. Now we need to delve into them a little bit more. So, depending upon which book that you're in, either speed of light either equals wavelength lambda nu, okay, this is the Greek letter nu, which means frequency, or you'll see it written as wavelength times frequency. It means the same thing. But here's what's important. Remember, these two are inverses of each other, okay? So as the wavelength becomes shorter, the frequency becomes higher. The wavelength becomes longer, the frequency becomes less. Now, so that was the first equation that we figured out in terms of light. The next one was figuring out the energy in a single photon. Now this is what's going to be important. This is the energy in a single photon. So to show you that light carries energy, and there are different spectrums, not necessarily the ones that we can see. So this is just a solar panel, oddly enough, that I have hooked up to a speaker. Okay, and what it does is that it transmits that energy that it's making into sound. Okay, so that's making kind of the staticky sound. If I put my hand over it, then it stops.
He's trying to flashlight straight onto it.
Well, we'll get to that. Okay, so you got sound, you don't have sound. Got sound. So what that is saying is like, oh, this is what. So the light that you're seeing is carrying a certain amount of energy. That energy is being transferred into an electric current. The electric current is being picked up by the speaker, it's being amplified, and you all then hear it as sound. So you're starting with electromagnetic radiation, you're changing it into sound, which remember, that's like the longitudinal wave. Now, here I've got your basic remote control, right? So if I point that at something, right, okay, theoretically this is sending out a signal, which obviously we can't see. But if I take this remote control and I point it towards the solar panel, okay, what it's doing, and this is a nice way to show intensity.
That's cool.
So if I start far away, you can't hear it. But as I get closer, it gets louder and louder and louder because that sound wave is being sent out in a wave, and that the amount of energy is remaining constant. But as I'm getting closer, then that has more, more intensity. So if I move away, now if I hit different buttons, okay, each button, we really can't hear the difference in terms of what we're able to discern in terms of sound, but each one of these buttons is emitting a different, slightly different frequency, which is corresponding to a slightly different energy, which is giving whatever is receiving that signal a slightly different command. Okay? So all of that, what your receiver is doing, whatever you're hitting with your remote control, whether it's your garage door, whether it's your TV remote control, whatever that is, you're sending an electromagnetic signal. And that receiver is picking up that amount of energy. And that is taking that energy and going, oh, I need to increase the volume. Oh, I need to turn off the television. Oh, I need to open up the garage door. Okay? So when you hit that button, that's just exactly what's happening here. You're sending that signal, and there is something that's receiving that signal, picking it up, translating it into some type of a command. Okay? All right. Now, let's go to the back, and we'll show a different way that you can look at sound.
And one over biology.
Light flashing? Yeah. Okay. So, what this is called a sound tube, and there's a piece of paraffin on the end of it that's sensitive to changes in pressure. So we'll play a little music, and we'll see what sound looks like.
Where we can be alone. The next move moving on. Me, yeah, me.
Yeah, my
Next
dad's
move moving on. It was with me, yeah, me. Singing, I love rock and roll. Putting all the time in the jukebox, baby. I love rock and roll. Putting all the time and dance with me.
So what you'll see is that it actually generates like a sine wave at certain points, well, because you have that just compression and rarefaction within the tube.
Next we're moving on, who's with me, yeah me, and we'll be moving on and singing that same old song, yeah with me, singing I love rock and roll, so put another dime in the jukebox, baby.
Yeah, so if you want to change it up a little bit.
I love rock and roll, so come and take your time and dance with me. I love rock and roll, so put another dime in the jukebox,
Maybe
baby.
something a little bit more mellow. Little James Taylor.
I know, I like how these are the songs.
Huh?
I said I love how these are the song choices.
I play Take It Off for
What?
Take It Off.
There's not very much bass.
Way down here, feeling fool, running your stateside games, lose your load, leave your mind behind.
Yeah, quick money rock this.
Mexico, the sounds so simple, just got to go. The sun's so hot, I got to
So a little bit of
Yes, I'll have to go down. American, not the sleepy eye.
so here's kind of my theme song. ZZ Top.
Like the Lowe's theme song.
This is back when rock and roll was actually good. Okay. All right. So, notice that plays out differently.
Where does the, oh, I see.
Yeah, there's just tiny holes that are drilled at the top. Okay.
The fire alarm goes off.
No, that would be bad. That would be very
That'd
bad.
be kind of, how would you explain that to them?
Okay, so on your, is that flashing? Tell me if that is.
Yeah.
Okay, thank you. All right, so there's different versions of this known as Planck's constant. So what this number tells you is it allows you to calculate the energy in a photon. So clearly, as your frequency gets higher, your energy gets higher. So there's an inverse relationship between like wavelength and frequency, but there's a direct relationship between frequency and energy. Now, depending upon what you're given in the problem, a lot of times you'll see this written, because if you take this and solve for frequency, so it's wavelength divided by frequency, or excuse me, wavelength divided by wavelength, excuse me. Frequency is the speed of light divided by wavelength. If I threw combinations together, eventually I'd get it right. So, sometimes you'll see this written as hc over lambda. Now, depending upon what information you're given, sometimes it's handy just to use this as Planck's constant, 6.63 times 10 to the negative 34 joules seconds. So what happens is, because frequency is 1 over seconds, the seconds cancel out, you get joules. So obviously that's going to be a pretty small amount of energy per photon. Now, if you look at what happened for Ryan to pop popcorn, okay?
I didn't do that.
Huh?
No,
There's no popcorn.
there's no
over
popcorn here.
Okay, there was.
No,
No, it's kettle corn.
never in.
Kettle corn? Oh, that's even worse.
You
Okay,
did not cook popcorn
kettle corn.
while you were playing
So,
your instrument.
What happens in a microwave is that you're taking that energy in the form of photons that you can't see, and that is superheating the water, the popcorn, whatever that is, and basically it's making those particles vibrate. So you're dumping energy into it, it's making those particles vibrate. As they vibrate, they generate heat, voila, you get kettle corn, okay? Or you get a cup of hot water for tea, whatever that's going to be. Now, on the yellow sheet that you're going to have, you're actually going to see different versions of Planck's constant. So what you're going to see on there is 6.63 times 10 to the negative 34th joule seconds. You'll also see it written as 4.14 times 10 to the negative, screw that up, times 10 to the negative 15th electron volt seconds, okay? Because if you remember, electron volts is how much energy it takes to take one electron and accelerate it through a voltage difference of 1 volt, okay? So if you look at, that relationship, so that's another way that you're going to measure energy. So if you're given the frequency of light, and it says, hey, what's the energy of that photon in electron volts? Then just use this value right here, because that's already in electron volt seconds. The seconds cancel out, then you get electron volts, okay? Now, the other version that you will see when you have HC, you can get 1.99 times 10 to the negative 25th joule meters. And that's also 1,240, 1.24 times 10 to the third electron volt nanometers. Okay? So if you're going to use this if you're given like a wavelength. If it says, okay, hey, a particular type of electromagnetic radiation has a wavelength of whatever that is, and you want to find the energy, okay? So if you're given that energy, or that wavelength, and you want to find that, you go, okay, well, E equals hc over lambda. So if your wavelength is in meters, and you want to find the energy, just do this, okay? That way it saves you the hassle of finding the speed of light and finding the frequency and plugging it into the traditional equation. So this just saves you some heartache. This one is electron volt nanometers. So a lot of times, because wavelengths of light are pretty small, so if it might, like visible light might have a wavelength of 600 nanometers. Okay, so if you want to find the wavelength in one particular photon and the wavelength is in Newton meters, just use this because it's already in electron volt Newton meters. That just saves you that hassle of doing this. So just be familiar with this. This is on your yellow sheet, okay? If you really want to get fancy, you can store all these in your calculator, okay? It'll save you some time, but anyway. So I just wanted you to see where all these equations come from. All right, now let's talk about intensity. So power is measured in what units? Watts. Your area is going to be typically in meters squared. So if it's a point source and it's radiating out that energy in all directions, to calculate that wavefront area, y'all have seen this before, but that's 4 pi r squared. Okay? So that's if it's, you have like a beacon and it's radiating that energy in all directions. Now, if it's like a laser, and you're going to talk about the energy concentrated on a particular point, then that would just be pi r squared because it would just be the area of that dot. Okay? But generally, how it's going to play out, like the sun, for example. Okay, hey, the sun's emitting energy in all these directions. So, but again, think about this. If I look at this remote control, okay, and it's sending out, okay, so it's sending out this signal. So the power coming from this is a fixed value. But as it radiates out from that remote control, what's going to happen to the intensity of that light? It's going to decrease. So, and that's the cool thing about showing this, is that as I move this further away, it becomes weaker and weaker and weaker. So this is also why, you know, if you go out into the parking lot, and let's say you live at, I don't know, 119th and 21st Street, okay? You go out there and you hit your garage door opener, guess what? It's probably not going to open up your garage door, okay? And it isn't because it isn't sending out a signal, but it's just so weak that it isn't going to cross that threshold. So that's what one of the things you can do when if you're going to get bored. It's like, just how far away can I be and still have that garage door opener work, or with your remote control or anything? Because what's going to happen is that there's a threshold, and if that intensity is below that threshold, then it's not going to activate it. But if you're within that threshold, then you hit the garage door button. Oh, the garage door comes up. Same thing with your car. Okay, if you're like does anybody have like a proximity key? Okay, yeah. So if you're too far away from your car, it isn't that it isn't getting the signal, but it's just that it isn't above that threshold to allow you to open up that door. Okay, so anything with a remote control is going to operate off that principle. There's a minimum threshold that has to be met. Okay, now. And these next equations I'm going to write down, they're in your book. If you need them on the test, I will give them to you on the test. But this is just going to be a bigger idea. And there's a different way to calculate these intensities. And I in no way expect you to memorize these. But I'll show you where they came from in just a second.
B or P?
Hold on. That's a B. It's your magnetic field.
See the current? How did the chicken?
Okay. So, what you'll see, and I've got some videos that are going to show this, just because the graphics are much better than I can draw, okay? So, the other way that you can look at intensity, and they both involve the speed of light. So this is that epsilon naught So on your equation sheet, so on the back side, you have your epsilon naught, which is, where's epsilon naught? Your vacuum permittivity, 8.55 times 10 to the negative 12 coulombs, newtons per meter squared. And then you have the vacuum permeability, which is at 4 pi times 10 to the negative 7 Tesla meters per amp. So these are constants, okay? So here's the main idea. This is all a constant. This is the speed of light multiplied by a constant. This is the speed of light divided by a constant. So what you'll see is that, and this is where you study electric fields before you study light, is that just like if I have a current and that has moving particles, that generates a magnetic field. The other side of it is that we've just learned that if you have a changing magnetic field, that induces a current. So light is a combination of it's called electromagnetic theory, because there's an electric field to it and there's a magnetic field to it. So here's what I want you to see, is that as the electric field becomes stronger, the intensity of the light is going to become stronger. As the magnetic field portion of the light becomes stronger, your intensity is going to become stronger. Okay? So this is just a constant, this is just a constant, but this epsilon naught is your electric field component of it. This is the magnetic field component of it. So here's all I want you to get out of this, is that if you increase the electric field, you increase the intensity. If you increase the magnetic field, you increase the intensity. So I've got a couple of videos to watch here. And I'll admit, the guy doing the explanation is a little eccentric, okay, but the graphic, I'm just showing you this because of the graphics, which is better that I can draw, and it's important that you get that visualization. So,
Thirsty.
I was just going to say, my God.
It's not my fault. It's loud.
Hey crazies, sometimes math is unavoidable. Without it, you miss out on important insights. So what if, instead of avoiding math, we try to visualize it? I want to give you a glimpse inside my head for a few minutes.
Okay.
This episode was made possible by generous supporters on Patreon. Okay, so the math I want to help you visualize today is divergence and curl. But this isn't a math channel, it's a science channel. We need context. Fluid flow seems like an obvious choice, but those aren't always simple like this. Sometimes they're rather complicated.
It doesn't.
And if we're being honest, I don't really understand fluid mechanics as much as I'd like to. I'm trying to teach myself, but that takes time. So we'll reserve fluid animations like this for analogies only. Let's focus on something I happen to know a lot about, the electromagnetic field, which is actually a combination of two different fields. An electric field, shown in blue, and a magnetic field, shown in orange. We did a whole series on how we discovered those fields and what they do, but I didn't talk about divergence and curl at all, and I think that was a mistake. So it's time to fix it. We have two behaviors, divergence and curl, acting on two different fields, electric and magnetic. That means we need four equations. They look something like this, the Maxwell-Heaviside equations, which most people just call Maxwell's equations. Don't get me started. But these constants are just there to make the units work out. They're not actually
So there's your
important for
epsilon naught.
understanding the equations. So
And there's
let's
mu
set them
naught.
all equal to 1. Do what I want. Alright, as we go through these one at a time, we'll look at the equation first, and then we'll see what we can do about making it more visual. Let's start with this one, also known as Gauss's law. It says the divergence of the electric field at some point equals the charge density at that same point. In other words, the reason the electric field isn't just zero everywhere is because electric charge exists. But this law tells us something about the shape of the field, too. Say we draw an imaginary sphere around some region of space. The outer surface of that sphere has electric field arrows sticking in or out of it. Since that sphere is imaginary, we can make it any size we'd like. But to find the divergence, we need to make that sphere really small. Like, just a bit larger than the size of a single point kind of small. You're such a little adorable sphere. Yes, you are. Yes, you are. Anyway, the divergence of a field tells us how much that field points away from that tiny sphere. If the field points into the sphere as much as it points out, then the divergence is 0. Gauss's law tells us there's no charge at that point. If the field points more out of that sphere than in, the divergence is a positive number. Gauss's law tells us there's positive charge at that point. If the field points more into the sphere than out, the divergence is a negative number. Gauss's law tells us there's
Because
negative
that, a
charge.
positive test charge will go
Electric
in that
charge
direction.
is the reason the field looks like that. Of course, that's all very static and a little boring. If it helps, you can imagine this electric field is the velocity field for some fluid instead. That way it's easier to see the inward and outward directions at any particular place. But it's important to remember this is just a visual tool. Nothing is actually flowing in this picture. There's no electromagnetic fluid. It's not a thing. We can interpret the other divergence equation the same way. It says the divergence of the magnetic field at some point is always equal to 0. So unlike with electricity, there's no such thing as magnetic charge. In other words, there are no magnetic monopoles. Magnetic poles, like north and south, always come in pairs.
That's going to be important.
Consider
You
the
will always
magnetic
have a
field around
north
this
and
bar
south
magnet.
pole. So
Using that
you
same
can't talk
imaginary
about like
sphere,
a
the
north and
divergence
south
is how
electric
much the
field.
field points away. Since the divergence of the magnetic field is always 0, there is always just as much field pointed into the sphere as there is pointed out of it, no matter where we put that sphere. This becomes pretty obvious using the fluid analogy. Every streamline that goes into the sphere comes back out. That's all there is
As
to
long as you're
divergence.
not moving the
The
magnet.
curl, on the other hand. Why does this keep happening? Curl is a different story. Your first instinct might be to imagine those closed fluid loops again. And that's certainly an example of a curl. But this flow has a curl too, without loops of any kind. That's because the curl isn't really about the field itself. It's about what the field might cause. In this fluid example, say we draw a tiny imaginary circle somewhere on the screen. Oh, come on, man. If we imagine some kind of paddle attached to that circle, the difference in flow between the top and bottom will cause it to spin. So even though the field itself doesn't circulate, the things inside it will. Now
So
let's
that's
get back
like
to
when you do the
electromagnetism.
calculations with the loop.
Faraday's law says the curl of the electric field at some point equals
those
the
of you that
negative
are
charge
counting
of the
this
magnetic
notice.
field at that same point. Say we draw a tiny imaginary circle again, and we notice a magnetic field passing through that circle. If that field is changing over time, Faraday's law tells us there must be an electric field that curls around the imaginary circle. The curl
So
of that
this
electric
is
field
your right hand
opposite
rule in
of the
effect,
change of the
right
magnetic
here.
field.
So as
But
that
remember,
current
the
changes
curl isn't
direction,
about the shape of
the
field.
direction
It's
of
about
your
what
right
the
hand
field
is going to
might
switch,
cause.
and that's why that
If our
current goes
imaginary
back and
circle
forth.
happens to be a metal ring, we'll get a circulating current. That result is what matters. So where was I again? Divergence of the electric field, divergence of the magnetic field, curl of the electric field. All right, there's one equation left, the curl of the magnetic field. It's pretty obvious from the bar magnet example that the magnetic field curls. But let's take a look at Ampere's law and see what it actually says. A curl in the magnetic field at some point can happen for one of two reasons. An electric current passing through that point, or a changing electric field at that point. It's the longest of the four equations, which is why I saved it for last. Don't panic, we can handle this. Say we've got an electric current in a wire. If we draw our imaginary circle...
So notice that that current is going down,
Ampere's law
okay?
says the magnetic
Notice that
field should curl
notice that
around
that current is
circle.
going around in
Now
that
let's say
direction.
somewhere along this wire, we've got a capacitor. It'll act like a gap in the circuit, which means no steady current, which means no field. Unless that current is alternating.
That was kind of cute.
Alternating current, or AC, opens up a lot of possibilities for us. Since the current in the wires is changing on either side of the capacitor, the electric field inside the capacitor is also changing. That changing electric field creates a curl in the magnetic field around our circle, just like the current does in the wire. This keeps the behavior of the magnetic field smooth across the entire picture. There's a curl in the magnetic field all along the circuit chain. So, what's the best way to visualize Maxwell's equations? Using tiny imaginary shapes and a little imaginary fluid. Divergence tells us how much a field points toward or away from a point in space. For electric fields, that's caused by charges. For magnetic fields, it's always zero, so we know magnetic poles always come in pairs. Curl tells us which way something inside the field might spin or circulate. In electrodynamics, that means we'll probably get some kind of electric current. Just remember, those shapes are imaginary, and that fluid isn't really there. They're just tools to help us visualize the math.
Okay.
So, what do you think? Should I do more videos like this? Please
No.
share your thoughts in the comments. Also, maybe answer the poll that pops up over here somewhere.
Okay.
If you want to see the actual math of divergence and curl,
No, we don't.
there's a whole chapter in my ebook on vector calculus. Big new.
Okay.
He does like it's oddly.
I've achieved shit.
Are you still running on spice? Amanda, mine looks.
You know, if it was daytime, I'll move to Iraq. I'd rather live in that university. Oh, man.
Yours just looks like surprise.
It's in rock. When was the founder explosion? Like the 70s?
That just looks bad.
When was the World Gulf War? Like the 90s? Exactly. Obviously, like I say, you're raised the generation that went to the Gulf War. Congo saw him been alive. Attack 9/11. To attack 9/11. Attack 9/11.
One of his hands is fine, the other.
So that big for raising the children.
The other one's like tiny and like.
Killed and tried to kill Saddam Hussein.
Do you think they'll like roll out?
Okay. So here's the next
All
one.
the children, little kids, killing machines. Americans who died in the Salvation Army.
Oh, seriously?
Is it like some tackle like more Americans died? Like celebrating.
Why didn't I play what I wanted to play? You would think it would have clicked on the one that I just had. God, that was a struggle.
Our band, Matt, This episode was made possible by generous supporters on Patreon. Hey Crazies, I've made a particular statement several times in this channel. Light is an electromagnetic wave, a disturbance in electric and magnetic fields. Which begs the question, huh? What does that even mean? Well, let's start from the beginning. No, stop that. We've talked about this. Stupid AI. I mean from the beginning of our most recent series on electrodynamics.
No.
Whenever it's possible, we try to treat the electric and magnetic stuff separately. If there's a charge, there's an electric field. If that charge is moving, there's also a magnetic field. That's two separate fields, the electric field and the magnetic field. And people spent the majority of the 1800s trying to describe how they work. To the timeline! In 1835, Gauss's law showed us electric fields came from charges. In 1820, Ampere's law showed us magnetic fields came from moving charges, both confirming what we covered earlier. Bingo bango, mystery solved, fields described, end of story. Wait a minute, that can't be the whole story, right? I mean, we've seen other laws in this series. There was a Gauss's law for magnetism too. And in 1831, we got something called Faraday's law. That brings the equation count up to 4. Each of these laws says something about at least one of these fields. Gauss's law for electricity says electric fields point away from positive charges and toward negative charges. Gauss's law for magnetism says magnetic fields always form closed loops. Ampere's law says those closed loops wrap around a moving charge. Faraday's law is the odd one out on this list. It seems to connect the fields to each other. Basically, a changing magnetic field makes an electric field. Wait. One of the fields can make the other field? Yeah, it's pretty weird, isn't it? Come to think of it, this is kind of a big deal. If one field can make the other field, then maybe the charges don't make the fields at all. Maybe they just affect them. Maybe they're a thing all by themselves. I mean, we said light was a disturbance in electric and magnetic fields, and light is a thing all by itself. So it makes sense. In fact, that's exactly how we imagine fields these days. Notice the arrows in this graphic remain in place as the charge moves. They're attached to the space, not the charge. If there aren't any charges around, we like to imagine the fields are still there and just have a value of 0. We really wouldn't get confirmation of this, though, until the 1860s. Back to the timeline. 30 years after Faraday, James Clerk Maxwell enters the conversation. He thought to himself,
a changing magnetic field affects the electric field. The next changing electric field affects the magnetic field. Yes, they should be able to affect each other.
So he took Ampere's law and tacked on an extra term to make it happen. Did he just invent that out of thin air? No, not really. I'm lying a little bit. He wasn't that haphazard about it. He did imagine a conceptual model first, with a sea of tiny molecular vortices. That model was horribly wrong, but his result turned out to be correct anyway. The lucky son of a... Anyway, Faraday said that a changing magnetic field gives us an electric field. And now Maxwell's saying that a changing electric field gives us a magnetic field. The circle is now complete. This discovery had profound consequences for our understanding of these two fields. But Maxwell kind of fell short in this department. His versions of the equations were kind of a mess. There were literally 20 of them. With vector calculus, we can combine some to shorten the list to 8, which makes Ampere's law a little more obvious. But Maxwell wasn't interested in being concise. He was an experimentalist and wasn't super great at deep truths. It wouldn't be until Oliver Heaviside arrived 20 years later that we actually get the equations everyone knows. And yet somehow, these equations are called Maxwell's equations. History is a cold-hearted monster. Anyway, the point is, we've described a way for these two fields to affect each other. Back to the timeline. Maxwell thought about this connection for a few more years. Then suddenly, something occurred to him.
If a charge of the velocity gives us a magnetic field, then a charge of a changing velocity gives us a changing magnetic field.
That's when Maxwell saw the light. Like, literally, he rediscovered light. We know from Faraday, a changing magnetic field gives us an electric field. If that electric field is also changing, then we get a magnetic field, a changing magnetic field, which gives us a changing electric field, that gives us a changing magnetic field, that gives us a... You get the point. Maxwell had discovered electromagnetic waves, and when he calculated the speed of those waves, he found it to be a constant 299,792,458 meters per second, the speed of light. And it's not just about light. That's the speed at which any change happening with the charge can be communicated to the field. There's a delay between when the charge moves and how the field responds at all these points in space. It's difficult to see with this graphic though because everything is happening so fast. We need to zoom way out and slow the speed of light way down to get a better view. Let's imagine a radio transmission tower. Inside the tower, charges move up and down. Since that's a type of acceleration, the magnetic field is changing over time. The field arrows nearby respond almost immediately, but the ones farther away don't respond until later. The speed of light demands that there be a delay. In a way, the field arrows are responding to where the charge was in the past and what it was doing back then, rather than where it is and what it's doing now. The result is a wave pattern, which we usually write using sines or cosines. We just evaluate each arrow in the field at an earlier time, depending on how far away it is from the source. That's why we give this extra term. But math aside, let's just stop and appreciate something for a few seconds. This field disturbance is self-sustaining. You can stop the charge from moving, and the fields will continue to do this. There's now a disturbance in a couple fields that travels out through space.
Now,
All
here's-
because some charge accelerated at some
Here's the cool part about this. Is that once you start it, then it becomes self-perpetuating. So this is what allowed us to get rid of this idea of the ether that exists between the sun and the earth, or between any source. So you don't have to have a medium. Like to have sound, you have to have something to transmit that. So once you start it, then it becomes self-perpetuating. So this is the cool part about electromagnetic theory, is that it's just this self-perpetuating thing. A disturbance in the electric field creates a disturbance in the magnetic field, which creates a disturbance in the electric field, which creates a disturbance in the magnetic field. So this is why it's called electromagnetic theory. So here's the whole part of this, is that once you get it started, it will continue on its own. Okay?
in the past. And that field disturbance is what we call light. So, have you seen the light? Let us know in the comments. Thanks for liking and sharing this video. Don't forget to subscribe if you'd like to keep up with us. And until next time, remember, it's okay to be a little crazy.
He is a little bit.
Except for the...
He's got cool videos. That's the only reason we do that. Okay. All right. Let me turn my on.
No. Shut up.
I slept 3 hours last night.
What?
I think I slept 3 hours last night. I don't even know how late it is.
Okay. So here's the deal. So here's like the simplified version of those equations that he just gave you in terms of what you're going to be able to expect to know. So out of this, here's what we figured out. Is that the electric field is equal to the speed of light multiplied by the magnetic field. So here's the deal. So your speed of light is a constant, right? So this is what's going to be important. This number isn't going to change. So if you ever know either the strength of the magnetic field or the strength of the electric field, you can automatically find out what the other one is. Now, the other thing that happens is because the speed of light is a constant, and it goes back to this whole idea that as if your magnetic field, the strength of your magnetic field doubles, so in other words, if you double that change in that magnetic field, then correspondingly, you're going to double the change in the electric field. So it isn't like it's an inverse relationship. So if you ever increase one of them, you're automatically going to increase the other one because you're multiplying it by the speed of light. So what James Clerk Maxwell was able to do, this is where he was able to predict the speed of light before they were actually able to measure it. So he came up with this, that here's your permeability constant and your vacuum permeability constant. And so if he came up with this and said, oh, the velocity of any type of electromagnetic radiation is going to be the inverse of these two values multiplied together. So they had known the values of this. So if you take these two values and plug them in, and then you take the square root of it, you get the speed of light, which is 3.00 times 10 to the 8th meters per second. So these numbers were just constants. But once they found the numeric value of those, then they were able to predict the speed of light. So what that did is that nullified the idea. It had two big impacts. It nullified the idea that the speed of light was instantaneous. Like, there is a value to it, okay? It isn't instantaneous. It's a big number, okay? But it isn't instantaneous. The other thing that did is that it got away with this whole idea of having to have an ether, where you had to have a medium through which you could transmit that electromagnetic field. So you have and this is an important part, you have an accelerated charge, okay? That accelerated charge, this is what creates radio waves, okay? If I press down on this button, right, to send a signal, an electron has to be accelerated somewhere to create that disturbance. Now, if I do this, and I just hit that like one time, I don't have to keep holding it, because as soon as that electromagnetic wave gets created, then it's going to create its own disturbance, which is going to travel through. So what we've been able to do, and if you look at everything that runs on electromagnetic radiation, okay, your cell phones, all of you, I'm guessing, have cell phones, right? Well, if you look at what has to happen for you to get a text message, so Ryan gets a text message, right? And the reason it doesn't show up on Diego's or Joel's or my phone is because that information is being sent with a very, very, very specific frequency, with a very, very specific amount of energy that's being sent to Ryan's phone. Now, all our phones are capable of picking it up, but it just doesn't resonate with our phone. So all of that information that you're getting via the internet through your phone, and it's a tremendous amount of information, okay? TikTok videos, which I abhor with a passion, text messages. Yes, sometimes you use your phone to talk to people. It's like, get out. It's like, people talk on their cell phones? I know, shocking, okay? It's like, really? How old-fashioned, okay? Send me a Snapchat. I don't want to hear your voice. Just send me something that I can ignore. So, don't act like that doesn't happen. So, here's the deal. So if you think about all of the information that's being transmitted via electromagnetic radiation across the world on a given day, it is a tremendous amount of information. But it's cool. Even if I go to Europe, okay, take my cell phone, I'm in Scotland, okay, driving around there. I'm still going to get the text messages. So even if I'm in Scotland, that information that's being sent to my phone is specific to my phone. I don't have to worry about somebody in Scotland picking up that signal. So if you look at all of the phones that exist in the world, and you talk about being able to subdivide a signal so that it's specific to your phone, that's a pretty cool process if you think that through, if you look at all the information that's out there. So one of the big debates in the universe is that, are we alone? So when you send out a signal, it just doesn't stop within our Earth. That signal keeps going. All the radio signals, TV stations, everything, we are basically this, in space, we are this huge electromagnetic lighthouse, okay? So we're sending out all of this information, okay, beaming it throughout the entire solar system, the Milky Way galaxy, everything. And that really became big in like the 1920s. So roughly for about 100 years, we've been broadcasting a tremendous amount of electromagnetic radiation. And oddly enough, that travels at the speed of light. So every year, we expand our, if you look at that equation, intensity equals, 4 pi over 4 pi r squared. So every year, that radius increases by a light year, and that's squared. So every year, the planets or civilizations or whatever capable of receiving that signal increases by a light year. And so one would, and this is the thought process, and there's an organization called SETI, which stands for Search for Extraterrestrial Intelligence. And what they do is they've got these big radio antennas, and they basically scan the skies, listening for signals. So that one would think that if there's intelligent life somewhere, and they've picked up our signal, unless it's maybe the Kardashians or something, and then they're just going to go, oh, screw you guys, you're stupid. We don't want to talk to you, okay? Sorry, not a Kardashian sister fan. Really don't see the point. So anyway, there's a whole bunch of really stupid things that they can pick up about our civilization. And one would think, though, if they have also achieved that level of technology, that they could send that signal back, okay? And so every year, you're expanding more and more that sphere that's capable of receiving this information and transmitting information back to us. And we've been doing this since like the late 1960s, 70s. Crickets. Absolute crickets. We have not found any other intelligible radio signal that exists that we've been able to detect, where they've heard it and they go, oh, let's get back with them. And they're not returning our phone calls. So, I don't know. Okay.
I like the South Park SpongeBob or something.
There's probably some alien out there watching SpongeBob or something.
Oh my God.
Like, what is this?
Hopefully not. Okay.
Please don't die. No problem.
Maybe they're so advanced we're not worth their time.
But don't tell them, like, don't give them names.
No.
Me and Amanda's are pretty close to aliens.
It's a lot of work.
Okay.
Get rid of that.
Delete.
Turn it off.
I didn't see those photons. You can't prove it, Brooke, yeah? So, anyway, so questions, and let's just make this due tomorrow, and then that way you don't have to worry about it being due after, then you all are going to forget a lot of this stuff anyway, that way it's fresh in your brain. And then so tomorrow we'll review, and then the magnetic test is on Wednesday. So,
Go over maybe tomorrow.